In continuity of the previous video, now we will prove the rest of the lemmas. So we will prove firstly lemma 2. So in lemma 2 we want to prove that summation chi p log p upon p over all the primes p less than equals to x, that is equal to minus l dash 1 chi into summation mu n chi n upon n for n less than equals to x. And here we will take chi, not non-principal character. Chi is not equal to chi 1. So we know capital lambda n, this is Mangold function, which is 0 for the numbers which are not prime powers, and for the prime powers its value is equal to log p. So we will start with this summation chi n lambda n upon n over n less than equals to x. So we will firstly derive this summation according to the definition of lambda. And now we know this lambda n is 0 if n is not a prime power. So only non-zero terms in this summation are the terms corresponding to n is equal to prime power. So we will write this summation as all the primes p less than equals to x and summation a varying from 1 to infinity where p raised to a is also less than equals to x. That means we are here assuming that n is equal to p raised to a for some prime p, that is it is prime power. So chi of n, which means chi of p raised to a, lambda of n, which means lambda of p raised to a, and we know lambda at any prime power p, that is equal to log p, so divided by p raised to a. So we here put n is equal to p raised to a, where p raised to a is less than equals to x for any prime p and a is any power varying from 1 to infinity. Now this summation chi p raised to a log p upon p raised to a, in this summation we will separate the term corresponding to a is equal to 1. So it will be summation p less than equals to x chi p log p upon p plus summation a varying from 2 to infinity chi of p raised to a log p upon p raised to a, and of course p raised to a is less than equals to x. Now this second sum on this right hand side, we will calculate only this. Firstly, let us say this equation number is let us say this is 8. So now start with this summation p less than equals to x, summation a varying from 2 to infinity chi of p raised to a log p upon p raised to a, this second sum on the right hand side. So now we know chi takes the values which are roots of unity or 0. So chi of p raised to a, this is always less than equals to 1. So we can write here this is less than equals to log p upon p raised to a. Now this log p, this is independent of a, so we can take this term outside this summation. So this is equal to summation p less than equals to x log p a varying from 2 to infinity 1 upon p raised to a. Now this is a GP series, so sum is p minus 1. So this is less than equals to, now this summation is sum over all the primes less than equals to x. So if we take all the integers from 2 to infinity and we replace p by n, then this sum over n, this will be greater than equals to the sum over the primes, because here this is sum of log p upon p into p minus 1, where these are all non-negative terms, and sum is over all the primes. So here sum is over all the integers, so that's why this sum is greater than equals to this sum. Now we know this series log n upon n into n minus 1, this is a convergent series. So if this is convergent series, so its sum is a finite quantity, and every finite quantity can be written as order of 1. So we write it order of 1. So now we put this value in 8. Then we get summation chi n lambda n upon n over n is equal to summation over the prime chi p log p upon p plus order of 1. So we can interchange their sides. So we get summation chi p log p upon p. This is summation chi n lambda n upon n over n plus order of 1. Now let us, this equation is 9. Now again we will start from the same sum which we have started, but in the different way. Now we know lambda n is summation mu d log of n by d over the divisors d of n. So again we start with the same sum. Summation chi n lambda n upon n over n less than equals to x, and put the value of lambda n. So it will be chi n upon n, and summation d divides n mu d log of n by d. Now d is a divisor of n and n is less than equals to x, so these two sums can be written as summation, if we put n is equal to dq, then these sums can be written as summation d less than equals to x and q less than equals to x upon d. Now chi n upon n, they will become chi qd upon qd. Now mu d becomes is log n upon d, this is log of q. Now we will separate. Now since chi is completely multiplicative, so chi of qd is equal to chi q into chi d, and we will separate the sums. The terms which are independent of q can be taken out this summation. So this term becomes chi q into chi d, so chi d can be taken outside. Similarly this d can be taken outside, and this mu d also can be taken outside, into summation q less than equals to x upon d chi q log q upon q. Now since x upon d, this is greater than equals to 1, because d is less than equals to x, so x upon d is greater than equals to 1. So the sum over q, for the sum over q we can use the formula that is proved in previous chapter. So we have proved this sum as such, and this sum can be written as minus L dash 1 chi plus order of log x upon d divided by x upon d. This is the formula proved in theorem 6.18. So this becomes minus L dash 1 chi summation chi d mu d upon d over d plus the order term, which can be written as summation d less than equals to x. Now in the order term, we know chi d and mu d both can take the values less than equals to 1, because chi d is root of unity. Either it takes the value whose mod is equal to 1, or it is 0. Similarly, mu takes value 0, 1 and minus 1. So both the numbers chi d and mu d, their mods are less than equals to 1. So in the order term, we can skip this chi d and mu d. So we can write, now this d will be cancelled with this d. So the order term becomes just 1 upon x into log of x by d. Yes. Now we calculate the order term. Now the order term is one by x summation log x upon d. Because this x is independent of d, so we can take it out. So this is 1 by x summation of log x minus summation of log d. Then this is summation of log x over d less than equals to x. So this is sum of log x and then sum of log x integer part of x times. So it is integer part of x log x minus, now this is log d over d less than equals to x. So this is log 1 plus log 2 up to log integer part of x. So this is just log of integer part of x factorial. So this becomes 1 by x. Now we have proved in earlier chapters that log of x factorial, log of integer part of x factorial, this is just x log x plus order of x. So put the value here. Now integer part of x log x minus x log x, this is a term which is less than equals to log x, because integer part of x minus x, this is mod of this is less than equals to 1. So mod of this term is less than equals to mod of this is less than equals to log x. And when we divide by x, this will be less than equals to 1. Similarly, order of x by x, this is order of 1. So all the terms can be written as order of 1. Therefore, now we put the value of order term here, and we get this summation chi n lambda n upon n. This is minus L dash 1 chi summation chi d mu d upon d plus order of 1. Now if we combine this equation with our previous equation, equation 9, then we get the required results. So let this be 10. So from 9 and 10, we can conclude that summation chi p log p upon p over the primes less than equals to x, this is minus L dash 1 chi d mu d upon d plus order of 1. So we can replace this d by n also. So this will be n chi n mu n upon n. So this proves the lemma 2. Now lemma 3. So in lemma 3 we want to prove that L1 chi into summation mu n chi n upon n over n less than equals to x is equal to order of 1 for non-principal chi So now we will use the generalized Mobius inversion formula. So we'll prove lemma 3. We will prove generalized Mobius inversion formula. So generalized Mobius inversion formula says if alpha is any completely multiplicative arithmetic function, then we have this G is equal to alpha circle F if and only if F is mu alpha circle G. That is Gx is summation alpha n f of x by n over n less than equals to x if and only if fx is summation mu n alpha n g of x by n. Now we put in this formula alpha n is equal to chi n because we know chi n is completely multiplicative function, and we put fx is equal to x. So we will get this x is equal to fx is x, so x is equal to summation mu n chi n g x by n, where what is g? G is summation alpha n f of x n, that means chi n into x by n. So we can take outside this x, n less than equals to x, chi n upon n. Now this summation n less than equals to x chi n upon n, this is summation from 1 to infinity chi n upon n plus order of 1 by x. So this becomes x into, now the summation 1 to infinity chi n upon n plus order of 1 by x, again by theorem 6.18 of previous chapter. Now this is L1 chi, so x into L1 chi plus x into order of 1 by x is just order of 1. Now we put this value of gx in this equation. So let us say this equation is equation 11. Now put in 11. So we will get x is equal to summation mu n chi n. Now gx by n. So gx is equal to x into L1 chi plus order of 1. So gx by n is just x by n L1 chi plus order of 1. So this is x L1 chi summation mu n chi n by n. Now order term. Now order term contains summation mu n chi n, and we know mu n and chi n mod of both the terms is less than equals to 1, so order term just becomes summation of 1 over n less than equals to x, and that will be less than equal to x, so this term can be written as order of x. Now if we divide whole term by x, then we get the required result. That means dividing by x, we will get this summation mu n chi n upon n. This is just order of 1, because when we divide by x, this left hand side becomes 1, this x will be cancelled, and this becomes order of 1. So order of 1 plus 1, this is just order of 1. So this is complete proof of lemma 3. Now we will prove firstly lemma 5, and then we use lemma 5 to prove lemma 4. So lemma 5. Again, in this lemma we will use once again the generalized Mobius inversion formula. So in this lemma we will put fx is equal to x log x, and mu the same chi. So we will obtain fx is equal to summation mu n chi n g of x by n, where g is summation chi n f of x by n, which means x by n into log x by n. So this becomes x log x. This log of x by n can be written as log x minus log n. So from the first term we can take this x into log x outside. So this becomes summation chi n upon n, now minus x into summation chi n log n by n. Again we will use the formulas proved in theorem 6.18. This summation chi n upon n, that is just summation 1 to infinity chi n upon n plus order of 1 by x, and this summation chi n log n upon n, this is summation 1 to infinity chi n log n upon n plus order of log x by x. So we'll put the values. So this is summation n varying from 1 to infinity chi n upon n, that is just L1 chi. So this is L1 chi plus order of 1 by x, then minus x, then minus L dash 1 chi plus order term, which is log x upon x. So this becomes, now in this lemma, in the statement of this lemma, we are assuming that L1 chi is equal to 0. So L1 chi is equal to 0, which means this term is 0. So we are left with only these terms, x into L dash 1 chi plus the order term. Now here the order term is x into log x upon x, that means order of log x, and here again the x is cancelled, the order term is just log x. So this becomes order of log x, and this term is 0 because this is given, L1 chi is 0. So now we have proved that x log x, now we put this value of gx, now we calculate gx is equal to x into this plus order of log x. So putting this value of gx here, so let us say this is equation 12. So put in 12, we get x log x is equal to summation mu n chi n into g of x by n, which means x by n L dash 1 chi plus order of log x by n over n less than equals to x. So this becomes x L dash 1 chi summation mu n chi n upon n plus the order term. Again mu n chi n takes the values less than equals to 1. So this order term is just order of summation log of x by n. So this is summation log x minus log n, and we have calculated this term earlier in the proof of lemma 2, this order term. So this order term becomes just order of x mu n chi n upon n plus order of x. Again we divide the whole equation by x and get the required equation. So dividing by x, we will get L dash 1 chi summation mu n chi n upon n. So this term when we divide by x becomes this. X log x is just log x and this is order of 1. So this becomes log x plus order of 1. So completes lemma 5. Now we will use all of these lemmas from lemma 1, 2, 3 and 5 to prove lemma 4. So let us prove lemma 4. Now in lemma 1, firstly we put h is equal to 1. In lemma 1, put h is equal to 1. So when we put h is equal to 1, we get this equation summation log p upon p over the primes less than equals to x which are congruent to 1 modulo k. So this will be 1 upon phi k log x plus 1 upon phi k summation varying from r 2 to phi k. Now here in lemma 1 we have the term chi r bar at h, but because we are putting h is equal to 1, so chi r bar at h which is 1 is equal to 1 because chi takes 1 at 1 because 1 is the identity element of the group. So we will skip that chi r bar h. So we'll write p x is p less than equals to x chi r p log p upon p plus order of 1. Now this sum over the primes less than equals to x. Now from lemma 2 this summation, now from lemma 2 this summation p less than equals to x chi r p log p upon p. Now because this r is varying from 2 to phi k, that means we are not taking here principal character. So from lemma 2 we have proved if chi is not principal character, then this summation is equal to minus L dash 1 chi into summation mu n chi n upon n over n plus order 1. Now from lemma 3, if L1 chi is non-zero, then this member summation mu n chi r n upon n, this is just order of 1 from lemma 3. This is order of 1 because if L1 chi is non-zero, lemma 3 actually proves L1 chi into summation mu n chi n upon n is order of 1. But if L1 chi is non-zero, and we know L1 chi, this is convergent series, so that will be just a finite number which is non-zero. So that summation mu n chi n upon n, that will be just order of 1. So firstly let us write the number of this equation, and let us say this equation is equation 13 and this is, let us say, 14. So if L1 chi is non-zero, then this summation mu n chi r n upon n, this is just order of 1, and this thing is by lemma 3. And second thing, if this is 0, then by lemma 5 this term minus L dash 1 chi r summation mu n chi r n upon n, this is minus log x plus order of 1. Actually, in lemma 5 we have proved this thing is equal to log x plus order of 1, but we are taking here with negative sign, so it is minus log x plus order of 1. So this thing is by lemma 5. So now we have two things. By lemma 3 we have this: if this is non-zero, then this summation is equal to order of 1, and if this is 0, then by lemma 5 we have this summation is equal to minus log x plus order of 1. Now in equation 14 we have this summation chi r p log p upon p is equal to this plus order of 1, but from this equation 13 here we are taking sum of this term from 2 to 5k, means we are taking the sum of this term over all the Dirichlet characters which are non-principal character. So for those characters chi r for which this is non-zero, because this term becomes order of 1, this term becomes order of 1, so from equation 14 this summation is equal to minus L dash 1 chi r plus order of 1, and because L dash 1 chi r, this is also convergent series, so this into order of 1, that is just order of 1, and plus order of 1, that again becomes order of 1. So from this we can say, if chi r is a character for which L1 chi r is non-zero, then this whole summation becomes order of 1. And secondly, if this is 0 for some Dirichlet characters chi r, for those characters this term becomes minus log x plus order of 1. That means this term becomes minus log x plus order of 1. So here we have to sum these terms from r varying from 2 to 5k, and we have assumed in lemma 4 that nk is the number of those Dirichlet characters for which L1 chi is 0, for which L1 chi is 0. That means this thing, this term becomes, so from all of this we can say this term, therefore 1 upon 5k summation p less than equals to x chi r p log p upon p, this term becomes 1 by 5k minus nk into log x plus order of 1, because the terms for which this summation is equal to minus log x plus 1, they are nk in number, so that will become minus nk into log x, and the rest of the term, and for the rest of the terms this is just order of 1, so we can write it order of 1. So this term of equation 13 becomes this. Now we put it in 13. Now putting in 13 we will get summation log p upon p for all the primes which are congruent to 1 modulo k. This is just 1 by 5k log x plus 1 by 5k minus nk log x plus order of 1, and the last term is order of 1. So we simplify this sum, that will be 1 minus nk upon 5k log x plus order of 1, because this 5k is just a constant, so order of 1 upon 5k is order of 1. So this completes the proof of lemma 4. So this completes the proof of theorem also. So now we have Dirichlet theorem. Actually Dirichlet theorem says there exist infinitely many primes in the arithmetic progression kn plus h, where h and k are co-prime, and that will directly follows from this theorem. So we can write here, this is our Dirichlet's theorem. If k is positive and h and k are co-prime numbers, then there are infinitely many primes in the arithmetic progression kn plus h. Obviously n is varying from 0, 1, 2, 3 and so on. So this proof of this theorem directly follows from the proof of previous theorem. Now we have one more theorem which relates the distribution of primes in arithmetic progression. Distribution of distribution of primes in arithmetic progressions. So let us firstly define this. If k is positive and a is any integer which is co-prime to k, then we define pi a. Pi a is number of primes which are congruent to a modulo k. That means summation 1 for all the primes p less than equals to x which are congruent to a modulo k. Actually we have defined pi x. Pi x is number of primes less than equals to x, and pi ax is number of primes less than equals to x which are co-prime to a modulo k. Now we know from Dirichlet's theorem that there are infinitely many primes if these are co-prime to each other. So it means pi ax tends to infinity as x tends to infinity. So we have a prime number theorem for arithmetic progressions which actually states that pi ax is asymptotic to pi x upon phi k, because earlier also I have told that for each reduced residue class there is equal contribution of the primes in each reduced residue class. So pi a is number of primes in the reduced residue class of a, and pi x is total number of primes. But we know there are phi k different classes, so we can assume that pi ax that will be asymptotic to pi x upon phi k, but we will prove it in the next theorem. So this will be phi k. Now we know pi x is asymptotic to x upon log x because of this prime number theorem. So as x tends to infinity, pi a is asymptotic to this. Obviously if a and k are co-prime to each other. And now we have this theorem. If the relation pi a is asymptotic to pi x upon phi k as x tends to infinity holds, if this relation holds for every integer a relatively prime for each a such that a and k are co-prime to each other, then pi a is asymptotic to pi b. So this is basically saying that number of primes in class A and number of primes in the class of B, they are just asymptotic as x tends to infinity whenever obviously pi a and whenever a and k and b and k they are co-prime. And conversely this also implies this. So let us say this equation 1 and this equation 2. Conversely 2 implies 1 also. So let us prove this. So one way it is obvious, 1 implies 2, it is obvious because pi a x is asymptotic to pi